everybody. I think we will go ahead and get started. I am Eric Jensen. I teach astronomy here, and I'm the chair of the Physics and Astronomy department. And I'm really excited to have our sort of panelists here today. I'll introduce them in a little bit more detail in a minute, but briefly, Derrick Pitts from the Franklin Institute, Eric Wilcots from University of Wisconsin-Madison, and Mae Jemison. So we're going to start out by each of our guests talking a little bit about what they do, sort of how they got to where they are, and I think they'll play off each other a little bit, and then we're going to hopefully try to make this into a conversation, and sort of, you can see what each of them has to say, but then I'm sure you have your own questions. I'm sure some new questions will be raised by that, and so we're going to have some presentation from them, but then plenty of time to open it up to the audience for questions. So Derrick Pitts is going to kick off for us. So Derrick is the chief astronomer at the Franklin Institute. He has now been there for 33 years, so he's a Philadelphia institution, I would say. And not only from that number of but I think any of us who have been in the area for any amount of time have heard Derrick talk on the radio, done wonderful programs on public radio on WHYY and on WXPN. And it's probably the case, I was thinking about this today, probably the case that if you ask people in the Philadelphia area to name an astronomer, he is the person they would name. And if you guys had to name a second astronomer, they probably wouldn't be able to do that. So I think he's our public face of astronomy, and really a great one to have. He's an alum of St. Lawrence University, where he majored in geology, and he's now a trustee there, as well as being a trustee at Widener University. Among his other media exposure, including his work on public radio, he's branched into a little bit more risky ventures, like appearing on the Colbert Report. We won't put you through quite as much of a grilling, I think, as Stephen Colbert did, but I encourage you to go check that out on YouTube. It's quite entertaining to watch. And he's a recipient of many awards for service to the community. And part of what they do at the Franklin Institute is open up their observatory to people to be able to see the night sky. It's really a great public service. And we were fortunate in this past couple of years to be able to join forces with the Franklin Institute and with a number of other institutions to coordinate our open observatory nights and to make sure for a period of time that there was no night where there wasn't a telescope available for people to observe the sky if they wanted to. And through Derrick's instigation, we're going to have a little reprise of that coming up here sometime this spring to do a little bit more public viewing. So I feel very fortunate as a scientist to have someone like Derrick, and have Derrick in particular, as someone who can communicate this to the public. Sometimes you hear somebody explaining your field and you kind of wince and you think that's not quite the way I would do it. And I'm always struck when I hear Derrick explain things about how it is so clear and so understandable, and yet not dumbed down. It's just right, and it's accessible to people. And so I really look forward to hearing what Derrick has to say to us today. So welcome.
Thank you. Good afternoon, everyone. It's a great pleasure to be here today to participate in this panel discussion, especially with my distinguished colleagues here. And again, I'll thank Eric for the invitation to allow me this opportunity. I think the way that I want to approach this is first to give you a little bit of background about how I got into this very interesting position where I am. I have what I think is a dream job, and if you had asked me 30 years ago when I was starting out in my career if I would be doing the kinds of things I'm doing now, there's no way I could dream up this position. It is both a broad, it's broad, but it's specific, and it is just so fascinating because I have the opportunity to meet and work with a great range of scientists of every level. I have wonderful opportunities to help connect people with science, particularly with astronomy, and I have this fantastic opportunity to pursue my own interests in science, in astronomy, and also in space exploration, space science. And I would never have imagined that that would have been possible through the position I have at Franklin Institute. It is the chief astronomer's position. I come to being the chief astronomer, as I tell people, by attrition. If you just wait for everybody else to die off, the opportunity opens up for you. But in fact, what actually has happened is that I've been able to fashion this particular position. When I came into the Science Museum business 30-some years ago, there was no real career for museum educators in the sense that I'm a museum educator, as I now come to realize that's what I really do. Because science museums at that time were only just beginning to feel themselves as a major broker for informal science education in communities across the country. And so these positions had not yet come into being. I began my work at the Franklin Institute, working in the observatory, manning the telescopes, and I worked in the observatory. I think I worked every day in the observatory for about 5 years. But I was a museum educator. I was an exhibits explainer, and eventually moved into becoming the main observatory and astronomy person simply by taking on all the astronomy programming that needed to be done in the museum programs portion of the museum's operation. Now you may wonder, how do I get to this from geology? Well, the way I get to it from geology is that I finished up all of my undergraduate geology work by halfway through my junior year. Had taken a bunch of physics and chemistry already for geology, and so I filled out the rest with astronomy, with physics and astronomy. And so by that method come to the work that I do in astronomy these days. It's a really wonderful combination background for me because I've always been interested in astronomy and space science. Always, 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 always. Maybe a little bit more on the space science side than the astronomy side, maybe. But once I really got into it, I realized that I'm dedicated to both of those pretty much full time. But the geology part works really well for me because it allows me to do something really interesting, and that is to have a really good, clear understanding of what's now called astrogeology. This mix of earthbound stuff with the spacebound stuff. So nowadays, when we talk about discovering extrasolar planets, I'm really in my element. And some of the early work that I did once I left St. Lawrence University at Franklin Institute was I did some work for NASA interpreting landforms on Mars. So I was a glacial geomorphologist. That's how I graduated from St. Lawrence University. So I'm a specialist in glacial landforms. I am a guy from North Philadelphia, broad and eerie, yet I'm a specialist in glacial landforms. But it really all comes from my pure interest and curiosity about the natural world. I have this deep and absolutely insatiable curiosity about how it all works. And it's not just the mechanics, although I love the mechanics. It's really about the beauty of how it all goes together. And from how it all goes together, the beauty of how it's manifested in so many different ways. Everything from the garbage that you see in a garbage pail that's rotting someplace, all the way out to the edge of the universe where we talk about the earliest galaxies now having been identified as the 600,000 years after the Big Bang being the most distant galaxies discovered, and the relationships between those two. Part of the reason why is because if we can understand the physics, if we can understand physics, we can understand how the garbage can be how it is, and how the galaxies can be how they are, and how they relate to each other across that whole thing. I think it's incredibly empowering for people to be able to understand this. And so this sort of brings me to my side of public education. You can tell how excited I am about astronomy and being able to observe the night sky, understand what's going on, and the beauty that I speak of. I really want everybody to be able to understand some piece of what I talk about when I say the beauty of all these things and how they work together. The reason why is because it enriches our lives to understand that stuff. On the other hand, it also does wonders for kids as far as empowerment is concerned when you teach a kid how to recognize Venus in the evening sky. The reason I like to use that as an example is because most adults have no idea how to identify a star from a planet. But if I can teach a 7-year-old not only how to recognize stars and planets, but how to identify specific ones, now this kid is imbued with some knowledge that most people around that kid don't have. And the kid feels better about themselves. And they begin to recognize that there is a world above their heads that goes on far beyond our atmosphere, way out to the edges of the universe. So then they begin to see themselves as being bigger than just where they are themselves. Right there, they begin to get a little bit of a peek out into that world. So the work that I do at the Franklin Institute Science Museum encompasses this whole broad range of teaching. So I do workshops for young kids. I do workshops for senior citizens. I do the National Public Radio stuff. You know, I do plenty of television stuff everywhere from, you know, the History Channel, the Weather Channel, the Science Channel, all this different kind of stuff I've done. And you know that I've done the work with Stephen Colbert, which was a real challenge to do. And, I also did some work with Craig Ferguson, twice now, if you know the Late Late Show with Craig Ferguson. Have you seen that show? Yeah, okay, it's wild. It's just wild. And I was explaining to Eric a very interesting aspect of that I'll tell you about briefly. And it is that, first of all, it's a challenge to be working with somebody like Colbert, because Colbert is very, very quick. He's very smart, very sharp, and he knows where he's going. And the trick for the guest is to be able to follow along and sort of keep up with this and stay on your feet. I'm sure you've seen instances where people get into trouble with Colbert and simply cannot extricate themselves. So he's licking his chops and rubbing his hands as he's sort of taking people apart. Well, for me, you know, we sort of got that straightened out early in the interview, so that was okay. But the experience, here I am, talking to Stephen Colbert, doing this program. So I've got to be focused on this program because I have to keep up with him. But at the same time, another part of my brain is over here going, wow, this is really cool. I'm in a studio talking, look at all those people out there. There's a camera over there, and there's this, and there's that, and all this, and so that was a really interesting experience to have. And what I really value about having done those is that I was able to bring my interest, my love of science, astronomy in particular, to an audience that might not normally be able to access that in that particular type of venue. So here we are now in a venue where you may not expect to have this happen, and this happens. You find someone who has a real passion about science and tries to push them to have a passion about science too. And so that's why that was a really great and wonderful thing to do. But at the base of this, it's that thing that I do at the Franklin Institute of using the informal science education platform to try to provide people with supplementary science information so that they can have a better understanding of the world they live in. I'm not trying to turn everybody into being an astronomer or being a scientist, but the point is that there are all sorts of things in our lives that require us to understand science. And if we cannot have that basic literacy in science, then there are many challenges ahead of us that are really going to bring us some difficulties. And I think Mae might chat a little bit about that. I'm not going to say anything more about that. However, I have had absolutely fantastic experiences coming from my training as a geologist, interestingly enough, just from the training of being a student, just from the exposure to the discipline of the science, which I really love, and I have been able to apply that and bring that to the work that I do at Franklin that now allows me to have access to all these different kinds of venues. For example, I've been to a number of space shuttle flights. I know a number of space shuttle astronauts really well, so I have a really interesting entree into that community, which is really great for me because in a sense, I'm really a motorhead. I love to know all the gory details about the engineering and all that other sort of stuff. I also have entree into the astronomical research community, so I know a bunch of people who are doing astronomical research at various places, so I really love that. And at the same time, I also have this connection to schools and basic public education. So I get to express and do my interest in all of these venues of science all the way across the board and bring that to a general public audience. I love to see the light go on in people's eyes when they get the concept, when they understand it, and their world has been expanded and opened. Okay, that's all I'm going to say for right now. Hopefully there'll be questions later, but we'll move on.
Thank you. Next up we have Dr. Eric Wilcots. So Eric grew up actually right here, not right here, but here in the Philadelphia area. And I knew he was a Philadelphia native when he came in yesterday after having fought a lot of snow, leaving Madison, Wisconsin, and going through Chicago to get here. And I knew he was a native when we were talking about our kids, and he uttered the phrase, "All public and parochial schools are closed." That was one of his favorite phrases growing up as a kid. And from there, on to bigger and better things. He got his undergraduate degree at Princeton and his PhD in astronomy at University of Washington in Seattle. Spent a few years at what astronomers call the VLA, the Very Large Array, which is a big array of radio telescopes in New Mexico. If you've seen the movie Contact or other movies, you may have seen this big field of telescopes that are out there. So I did some work there. And from there went to the University of Wisconsin, where he joined the faculty in 1996. I was just finishing up my graduate degree at Wisconsin then, and so that's when I had the great fortune of meeting Eric. And we have kept in touch. He's still on the faculty, but we've kept in touch since then. And so I'm very excited to have him here today to tell us about his work. So welcome.
Thank you, Eric. Thank you for the invitation. Thank you all for coming out this afternoon. So I'm going to talk about a slightly different path through my career to get where I am than what Derek has just talked about. And the amazing thing is that our paths actually cross. And that when I was in high school, I grew up in Germantown, by the way. But when I was in high school, I decided I wanted to volunteer at the Franklin Institute Science Museum. And so I walked into the Franklin Institute Science Museum, and there was Derek running the observatory. So Derek and I go way back, back to when I was in high school. And just as a funny aside, to tell you how small the world is, one of my scientific collaborators now, who's a professor of astronomy at the University of Arizona, was also working at the Franklin Institute at the same time. And she is now a professor of astronomy at Arizona, and we're writing papers together. So thanks to Derek. Thank you. So my path in astronomy started, and I think back to when I was a small child, and my parents, for some reason or another, bought me a telescope. They claim I asked for it. I don't remember asking for it, but they bought me a telescope anyway. And my dad has since said it was the best $50 they ever invested, because it got me hooked on doing astronomy and hooked on looking at the sky. One of the first things I did with the telescope, it was only a 2-inch telescope, but if you went down to the Franklin Institute last year or the year before when Galileo's telescope was there, you can actually see a lot with a 2-inch telescope. So one of the things I did was try to find Saturn, because you get a telescope, you gotta go and look at Saturn. It's got the rings, you have to. So I took my telescope out to the backyard, had my natural history magazine, I knew where Saturn was in the sky, pointed my telescope at Saturn, nothing. So I look again, pointed up again, nothing. And so I couldn't figure out what I was doing wrong. So I had this telescope, I knew where Saturn was, I knew what it was supposed to look like, supposed to have rings, and it didn't have rings. Now, as it turns out, every once in a while, from our vantage point, we see the rings of Saturn edge on. And when they're edge on, they're very, very thin, we can't see them with a 2-inch telescope. And Galileo actually claimed that he thought Saturn had eaten whatever it was that was around. And it turns out that when I was looking for Saturn, it was one of those years when the rings were actually edged on. So I was actually probably looking at Saturn and just didn't know it. But I kept at it, and then went on, as Eric said, to Princeton, got my degree in astrophysics, and then went on to grad school at the University of Washington out in Seattle. People always wonder, why do you go to Seattle looking at stars? It's cloudy there all the time. True, and so I made a decision. I remember when I was in my second year of grad school, as a graduate student, you've taken classes, you're kind of getting tired of taking classes. And what you want to do is you want to get into doing the research full time, because that's where the passion is. You want to figure out how something works out there. And I remember talking to my advisor, and he had a couple of different ideas. And one of them was to figure out how stars are forming in 2 nearby galaxies. I said, oh, that sounds cool. So the nice thing about it was I got to go to Chile. Twice a year, in January, the skies are clear. I left Seattle, went down to Chile, and did my observing from the southern hemisphere, and that was the first time I saw the southern sky. And the southern sky is absolutely beautiful, absolutely spectacular. And so you just get hooked on this. And so I did my thesis work down in Chile. And so again, growing up in Germantown, I would not have figured that I would have made my way to Chile, but there I was in Chile. And so then from there, I got a job opportunity at the National Radio Astronomy Observatory in Socorro, New Mexico, the land of enchantment. How many of you have seen Contact? You can see contact? Oh, very good. Excellent. Great. So the first part of it is in Arecibo, which is the largest radio telescope in the world in Puerto Rico. Another fantastic place to go. But the second part of it takes place at the VLA. No, we did not put headphones on and plug it into the telescope. Okay? I know Jody likes, she sat there with her headphones on the truck. Didn't actually work quite that way. But it was a great place to do science. And the nice thing about doing radio astronomy and then trying to convey that to both the general public and to students is it's a different way of looking at the universe. We are used to seeing the universe with our eyes. We look up and see the beautiful night sky. And even with telescopes like the Hubble Space Telescope, we are seeing one facet of the universe. But when you shift wavelengths, and now you have a radio telescope, the universe looks like a different place. And so, for example, if your eyes were sensitive to radio waves, and you went out on a fall evening and looked at the night sky, the brightest thing you see would be an object in the constellation Cassiopeia. It's a star that exploded several hundred years ago. It's the brightest radio source in the sky. That's what would stand out to you if you looked at the night sky with radio eyes. And so it's that ability to go into different wavelengths, see the universe in a different way. And that really, really hooked me into doing radio astronomy. And so I spent my time at the VLA looking at galaxies, figuring out how galaxies form. And one of the nice things about science in general, and this is something that I learned in an early age, is that you have the ability to see something that nobody's ever seen before, or to figure something out that nobody's ever figured out before. And that is really what keeps you going. And we see this in all disciplines of science and intellectual endeavor, that discovery aspect of it. That is really fascinating, and you get there and you get a new result and say, wow, that's neat, I wonder what it means. And then the fun starts. Then you start trying to figure things out. And so I remember once when I was at the VLA, I had the opportunity to be on the Bill Nye Show. And back in those days, I had these really big glasses. And so I embarrass my kids these days because apparently they showed this episode of Bill Nye in the high school. And so my older daughter, last year she was in high school. It's 2 years ago. She was a freshman in high school. She was trying to make the varsity soccer team, and she came home one day and said, "Dad, what did I do?" I said, "Bill Nye." I'm like, yeah, I was on Bill Nye. She said, "They showed it in the 12th grade class." So all these seniors she was trying to impress came up to her and said, "Hey, is your dad Eric Wilcots?" And so she was embarrassed to no end. So this is something that you can embarrass your kids with. Right, so but then I went on to Wisconsin, and I've been in Wisconsin ever since. And the great thing about doing astronomy in the university setting, and it's sort of the traditional way of where astronomy done is at the university, is you get to do a couple things. A, you get to do the discovery. You get to do the research. And it takes you places you didn't think you would go. You get to work with students, undergraduates and grad students, people who come in, they have a passion for doing science, and you get to mentor them. And you get to advise them, and you get to shape their careers. And professionally, that's actually what I'm most proud about, is to see some of my students, particularly the ones who walked into my office as a freshman and said, "Hey, I want to major in astronomy," not really knowing what it was. And now they're off having faculty jobs at universities, and that's really kind of a neat feeling. But you also need to teach students of all stripes and learn about what they're interested in, and give them that sense of empowerment that they can go home and tell their parents what they learned in Astronomy 103. They're not going to be astronomers, but they have a little bit more of an understanding of what science is, how science is done, and what science means. So it's an incredibly satisfying place to be in that university setting, to be engaging with students on research. And then the doors open. And a few years ago, we had a faculty meeting in the Department of Astronomy at UW-Madison, and we made a decision that we wanted to invest in a new telescope. We're a research department. We need telescopes to do our research. And the opportunity came up to join a telescope project in South Africa. We're like, wow, yeah, let's do this. And so we became partners with the South African government on building a 10-meter telescope in South Africa. And so there I was, on a plane, flying to South Africa, to work with folks on trying to set up the structure and the organization to build a telescope. And we are just about ready to get science coming out of the Southern African Large Telescope. And that has just been a fascinating experience, to go to a country that was sort of just starting out. And one of the things that struck me getting involved in that project is when, after apartheid ended and the new government came in, one of the things that government said, an official document, was that they were going to invest in pure science. Because investing in pure science, and South Africa has a lot of problems. There's things they can invest in. But to invest in pure science was a sign that they were an advanced country and that they were about to make a difference in the world. And so what did they pick? They picked anthropology and they picked astronomy. Okay? And so the South African government made a conscious decision to invest in astronomy. And right now they are bidding to build the world's largest radio telescope in South Africa as well. And so that has been an aspect of my career that when I was back at Franklin Institute, staring at the sun with our H-alpha filter, and I remember that, I didn't think I was going to be flying to South Africa, working with ministers in the government to try to figure out how to build a telescope. But that's what this career has done for me. And it's been absolutely fantastic. And one of the things I'm doing now, and I'll finish up with this, is a place you can go, is I'm also now the Associate Dean for Natural Sciences in the College of Letters and Science at UW-Madison. And so I get to see some of the things that Derrick was talking about. I get to meet faculty in all these other disciplines and going, that's really neat stuff you're working on. And to see just the vast array of what science is being done is absolutely fascinating. And so I'll end there. We'll turn it over to me.
Well, I'm incredibly pleased to have Dr. Mae Jemison with us today. After growing up in Chicago, she got bachelor's degrees in both chemical engineering and African and Afro-American studies at Stanford, a doctorate in medicine from Cornell, served in the Peace Corps in Sierra Leone and Liberia, and then joined NASA, served as an astronaut for 6 years, and in 1992 flew on the Space Shuttle Endeavour and went to space and became the first African-American woman ever to go to space. And as if that weren't enough, then since then she's done a whole mess of other interesting things. Founded 2 medical technology companies focusing on technology for the developing world, held visiting professorships at Dartmouth and Cornell, teaching environmental studies and teaching sustainable development, serves on numerous boards, awards too numerous to mention, including being a member of the National Academy of Sciences Institute of Medicine. And I just have to say, we tell our students liberal arts education, you can go do anything you want. It's incredibly inspiring to see somebody who has done that and done like all of it. Done all of these kind of things and brought, bridged across a huge range of interesting and exciting and really great things. And so I look forward to hearing more about it. So welcome, Mae Jemison.
I'm actually going to stand at the podium since I got to go last and chosen, and they're both from Philadelphia. I'm from Chicago, so do this way. And I actually was taking notes and actually listening to what they were talking about and how they were thinking about space and space exploration and how we got to it a little bit differently. So I want to share with you today some ideas that I have about space exploration, a little bit about my course going through. I'm not going to really give that much biographical, I did this, then I did that. But I want to tell you just a little bit about growing up and some of the ideas that helped take me through. And the first thing I'm going to say, because this is really central to growing up, and these are the things that I've learned. There are 86,400 seconds in each day. And each one of those seconds is extremely precious because we can do with each one of those seconds exactly as we please. But we can never get a single one of those seconds back. So it's what we decide to do with our time that gives it its infinite possibilities. And so I always want to thank people for allowing me to be there with them to share some of their time. And I think really hard about what I want to talk to you about. The first thing is, I want you to understand that, science and technology we know are critical to the world today. And lots of times we're hearing right now this whole STEM push, right? There's just everybody, you've heard now, everybody's familiar with the word STEM, science, technology, and mathematics. But what they end up doing is making it one into, we're just going to do competitive endeavors. Like, go into science so you can make the United States competitive. I'm not sure that would have worked for me when I was a little kid. I think it's the passion that you have to have, the reason why you're involved. So let me tell you who I am and how I got here. So I'm a way over 40-year-old African-American woman who is an engineer. I'm a wannabe dancer. I'm a medical doctor. I was an astronaut, a college professor, a struggling business owner. I'm a lover of cherries, chocolates, and melon. I'm a short-term pessimist, a long-term optimist. I'm a person who loves cats, but I absolutely hate to wash dishes. And I'm at my most optimistic when I think of myself. I see this little girl who used to lay outside on a summer's night on the south side of Chicago. And I would stare up at the stars with all my young imagination and intensity. And I would imagine myself there among them. Always assumed that I would go into space. I never had a time where I don't even remember when I started liking stars. I never had a telescope. But I loved thinking about space exploration. I was fascinated by it. And, you know, people say, you're growing up in the south side of Chicago in the 1960s. How could you, as a young African-American girl, imagine that you could go into space? Where did I get the audacity to imagine I could go into space when Alan Shepard, Scott Carpenter, John Young, Yuri Gagarin, John Glenn didn't look anything like me, to seem to share anything in common with me? I could because I was raised by parents who helped me to maintain my self-confidence. You see, it's that same confidence and motivation and creativity and energy that every child is born with. And I could see that humans share the desire to understand the universe around them. How could I see myself in space when most of the children in Chicago public schools at that time thought the engineers were the people who drove the train on the L tracks? I could because I could see myself there. Though others couldn't, I could see myself there. And I knew that I had the right and the responsibility to live up to my potential, to my ambitions. This is a piece that underlies all of this, our right to be able to be involved. And early on, I had to learn never to limit myself because of other people's limited imagination. And these days, I've learned never to limit anyone else because of my own limited imagination. I love the idea of space exploration. I read all kinds of science fiction books growing up, you know, from starting with the small ones, you know, from A Wrinkle in Time to going on to Colossus, the Forbin Project, Andromeda, which I think Contact is a knockoff of. But anyway, Andromeda Breakthrough and other things. I love science fiction movies. And, you know, I watched all of them, you know, in action movies. I Spy, Honey West, The Day the Earth Stood Still, Lost in Space, I hate it, Will. You know, and then there's Star Trek, original series Star Trek fan aside. I'm the only, well, I'm one of the few people who've actually been in space who was on Star Trek. I got a little small role. Anyway, I had a problem growing up with sci-fi movies. And this is the context I want to put this in. Because you already heard about some of the science, some of the backside of the careers and how you go into it. But I always had a problem with science fiction movies. Back in the 1960s, you guys are going to have to go with me with this. Because every time there was a woman or a person of color in the movie, they had a very predictable storyline. You all know what it was, right? As soon as the monster, danger, alien came, everybody started running, right? And the woman would fall, and somebody had to come save her, right? And if there was a black, yellow, brown person in the movie, they were killed at the very end, the beginning. So, I can verify to you that when I went up into space, that little girl used to dream of the stars in Chicago. She didn't fall down, and she came back down. And I have to also add something piece about, you know, why did I do the things I did? I didn't get away with being straight science oriented because my mother, who had been an English major in college, she was a school teacher, and she made me read other things. And in fact, at about the age of 15, when I was really getting great grades in school, she started correcting my papers. And even though the teacher said I wrote really well, I would give my mother my papers too, you know, because teenagers want to please their parents, right? They go about it in different ways, but basically teenagers want to please their parents. So I give my mother my papers already to be turned in. She had given them back to me filled with red ink. And when I was a senior in high school, she called me illiterate because she said I didn't have the groundings in the liberal arts that I needed to be a functioning, contributing member of society in all areas. And so that's the environment that I grew up in, and that's what helps to inform why I like to be involved. And that young girl is the most important, cherished part of me. She's who I want to be like most. You know, that's where I style myself. That's what I want to look for. And that young girl taught me one other thing. She taught me that a woman who strives to be like a man lacks ambition. I have to do a couple. This morning, I have the pleasure the next 2 weeks of being one of the official public delegates to the United Nations Conference on the Status of Women that's going on in New York this week and next week. And the focus of this session is women in science. And this morning, I attended a session that was on sort of science and developing countries. And one of the things that was very interesting is a number of folks spoke about the fact that women have traditional basic knowledge about science and technology that people often don't think to recognize, and that they've always used the science and technology in the works that they do in developing countries. And if you can build upon that, it makes a difference. So for example, you can talk about women know about water, they know about geology and all those kinds of things because they're the ones who are finding the water. So can you, if you're talking about building water wells or doing water engineering, use their knowledge base? But it brings me back to something else. You see, every group of people in this world have been excited about space and the stars. You know, so often when we think about astronomy and we talk about it these days, we think about it as something that is new. We talk about space exploration as though it's new, but it's not. It's been around for thousands of years. Because I think the most fantastic thing in space exploration is not the Hubble Space Telescope. It's not even Voyager being outside the confines of our solar system, which I think is way cool. I think the most difficult thing that I'm trying to figure out how people did are the first folks who started to track the stars in the heavens. How did they figure out that this star moved from last year to the next, or from 10 years ago to another time? Imagine the powers of concentration, of discovery, the memory that had to take place in order to get that right. And then to figure out all these other things. So I think sometimes we don't attribute enough to understanding how pervasive space exploration is to our beings as humans. People sometimes ask, why should we be involved with space exploration? And in fact, I had to really talk to myself when I got accepted in the astronaut program to figure out what kind of explanation I was going to give. Because people were asking, you know, you're spending all that money on NASA, why are we being involved in it? But here's the reality. It's something that's part of us. Space exploration has done tremendous things back here on Earth. I love the part about being there. I wanted to be involved. I love the part about reading about it, about learning about what's going on in the universe around us, you know, what's going on another star system, you know, how was the universe formed? That is very exciting, and I want to be a part of it. But why is it important? Why do we care? I think we care because as humans, it helps us find our place in the universe. I think one of the things that's critically important for us is to stretch out, to know, to try to imagine other things. I can give you some real practical reasons, right? One of the things I did in South Africa was to talk about using space-based technologies for healthcare. What are you doing? Using remote sensing for disease identification, being up above the Earth, being able to look back down, observe the habitat, and predict whether or not malaria will be in an area, whether or not there are cholera blooms and plankton. There are lots of different things you can do for remote sensing. We can talk about spin-offs, all those kinds of things. Everybody with their GPS now is very That stuff is in space, right? You know that, right? There are all these things that are very, very practical that we can point to, but if it was not for people sort of imagining what is possible, trying to actually get there, these things would never be a part of our world. So when we talk about South Africa looking at doing pure science, that is important because we understand that as we stretch ourselves, as we do things that don't have to involve dropping bombs, don't have to be worried, we can get on an adrenaline rush and we can make a very big difference in the future. I'm wearing a bracelet that says reality leads fantasy. I asked Professor Dorsey why she thought about being involved with space exploration. She said because she saw Lieutenant Uhura on Star Trek. Nichelle Nichols is one of my really good buddies. And this bracelet says reality leads fantasy. I always wanted to go into space, but you have to get the reality right to make the fantasies of tomorrow come true. You have to get the realities right now. Reality leads fantasies. The world that we're creating right now, the things that we ask our children to spend their time thinking about, is going to create their fantasies that they try to enact tomorrow. Thank you all.
Thanks to all of our panelists. And so what I'd like to do now is shift gears a little bit. You've heard a bit from each of our panelists, and so what I would like to do is turn it loose to you guys and see what questions you have. Who wants to jump in first?
Don't be shy.
Yes.
I'd like to direct this to Dr. Jemison first, but the rest of you may comment. What is your take on the future of space travel tourism?
Let me just jump in. I'm going to repeat some of these questions so that the people can be sure to hear them. So what's your take on the future of space travel tourism, right?
It's going to happen. I don't know exactly when. There are a couple of things that are loaded into that question. One is the whole idea of using commercial vehicles to get people back and forth to the space station now, which is what we're betting on. In some ways, if we're not going to continue to use Russian, if we don't be able to another vehicle. There are a number of different organizations out there already that are working on doing it. Some of them are talking about doing suborbital flights, which is where you go up and you sort of pass into space and you come back down really quickly. You don't get to make a complete orbit. I'm not sure that I would recommend that to anybody. Let me tell you why. You can say you're up there, but you might be nauseated a good period of the time that you're up there because the first couple of days that you're in space, you have something called space adaptation syndrome. So if I was going to spend my space tourism dollars, I'd want to be up there for a week or more. But I think that it's going to happen. I can't tell you how soon because a lot of the issues that are associated with going into space aren't necessarily going to be solved just because commercial entities now say they're taking it on. Those issues have been in place with NASA, and through commercial entities have really already done a lot, obviously, for getting humans in space. Probably it's about 10 years out, I would say, before you're staying up for long periods of time unless we co-opt the space station or some other things. Where we can let people stay up for longer periods of time. The other thing I can tell you right now, there's space tourism because there are people who actually pay to go up on the space station. I think sometimes, wow, that's really terrible because they're taking a seat where a lot of science could be done, blah, blah, blah. But I tell you what, if I hadn't gone into space and I had $25 million, I would pay it to go up. So, I don't know if you all have any.
You can go to my website where you can contribute $10. If I can get $10 people, I can get the $25 million to get to space station. I'll take a donation now.
Let me tell you about one other project that's kind of interesting. I don't know. It's just there's a group that's starting something called 100 Year Starship, which is way too long in the future and too far in the future for me. But it's basically how do we get the technologies and things in place that we can do interstellar travel within 100 years. which seems way too far off to me. The only thing I want to add on the whole space tourism, humans going into space, I'm trying to figure out how in the dickens did I manage to miss going to the moon? I mean, they were going there when I was this high. I managed to get in the astronaut program 40 years later, and they're still not doing it. I think it's a commitment we have to make when we talk about why do we do space exploration, why do we have humans involved. It makes a tremendous amount of difference to our aspirations and how we see ourselves as a species. I think it's that abstract, but it's also that concrete.
I think one of the reasons why you're upset about the 100-year project is because you want to be on that project.
Yeah, I'm working on it.
Good. The one thing I'll say about the space tourism idea is that while it certainly has it will certainly have its startup issues. Anytime you start any kind of new project, no matter how big or how small, there's always what I call startup jitters. There's stuff that has to get straightened out in the first period of operation. But what I find most intriguing about it is what it does for the general public. So if you don't have $25 million to get you to International Space Station, here's something else you can do. There will be, not too long from now, well, let me do it this way. If you don't have the $25 million to spend a week to 10 days on International Space Station, you can indeed spend, $200,000 and spend, like a half an hour or an hour or so going up to this ballistic flight that Dr. Jemison spoke of just a moment ago. But let's say you don't have $200,000 burning a hole in your pocket. Not too long from now, that price is going to be down to about $100,000 through another vendor that will get you up into the space experience. Yes, there is the space sickness part, but if you keep going down the pike, if you don't have $100,000, for $4,000, you can go to New York, you can go to Las Vegas, you can go to Orlando, I think it is, and you can jump on the zero gravity flights that will give you a day of training and an afternoon of flying ballistic curves in a 737 aircraft that will give you weightlessness for 30 seconds. And you get to do, 10 or 20 of those in an afternoon or something like that? And it makes you, it can also make you very sick. But my point is, the realm of space has actually only been available to those people who are really the best of the best of the best. And it makes sense because it's a very expensive endeavor and very, very dangerous to do this kind of thing. So you want the best people you can get to do that, present company included, no question about that. But what I love about it is the idea that it begins to stretch the imagination of everybody else and gives them at least the opportunity to think, maybe I can do part of this. All right, I can't be an astronaut, I don't have $25 million, but you know what? I could blow $4,000 and be sick for an afternoon and get to have some kind of sense of the experience of what it's like to experience zero-G. Okay, so that then opens the door for people to then become re-engaged with the idea that space travel is important for humans. And at every opportunity they have to engage to make something like this happen, that's the vote we need to make that happen. The thing I keep trying to get everybody to understand is that the space program is not NASA's determination. The space program is what happens when Congress and all of us tell Congress what we want to have happen. And then if we can really impress that and really prosecute that and get Congress to back a plan that makes sense in conjunction with NASA, then these things really can happen. But if Congress doesn't see that there's any interest in them on the part of the general public, money's not going to get spent that way. So if you're interested in seeing space exploration really happen as part of our government's initiative to push science and technology, that's where it has to come from. It has to come from us.
Okay, other questions?
Are you coming up with any more new models of a rocket ship?
Is NASA?
The question is, are you coming up with more new models of a rocket ship?
Okay, so I'm assuming NASA, I'd love to come up with new models of rocket ships, but I'm not an aeronautical engineer. But so here's the issue with rockets. there are different types of rockets. You can talk about rockets that have people on board or rockets that don't have people on board, and they're very different. The reason why they're different is because when people are on board, the rockets have to be safer, and they also have to have what's called they can't be as rough, okay? Because people are a little bit more fragile than some of the equipment that's sent up on vehicles that don't have humans on them. So there are a number of people who are engaged in, a number of companies and organizations who are engaged in building both kinds of vehicles. So we talked about NASA has a program now where they're looking at trying to build different types of propulsion systems. Propulsion systems are what actually gets the rockets up off the ground. They're the ones that give it its oomph. Remember seeing pictures of the space shuttle? And you see all the flames and everything coming out the back. That's the propulsion system. They have two of them. They have a solid rocket boosters, which are the big white ones on the side, and then they have the ones that are on the shuttle itself that actually are fed, the fuel is fed out of that big orange tank that's on the belly of it. That's one propulsion system. If you can go back and remember Apollo 13, right? They have one big single cylinder with lots of engines on the back. That's another propulsion system. So there are lots of different kinds of propulsion systems. The big issue, the big question we have now is how do you create a propulsion system that's going to get you to places like Mars faster, right? Faster than 6 months, faster than a year, because I want to go, but people run into problems if they stay in space for long periods of time outside the Earth's atmosphere. They get exposed to lots of radiation, other things. So you want to make them go much more quickly. People also, if they're not weighted down in a gravity environment, while we're walking around, we're building bones, our bones stay strong. When you go out into space, your bones start to deteriorate because they're not weighted down. So the bones said, well, I'm absorbing and laying down bone, but I don't have any work to do. I'm not carrying a weight around, so you basically get absorption, the bones get weak. So there are lots of things that can happen to people in space. So propulsion systems are one of the things that NASA's working on. That was what was in that budget that came through last year, where there was a big hubbub about Constellation, which was supposed to be going to the moon. It was left out, and they talked about putting in new propulsion systems. That's one of the big issues with designing rockets, is how the propulsion systems work. The other issues are how to protect humans, how to protect the payload, where it needs to go. So there are a number of different things, and there are lots of people working on different types of rockets. But right now, there is not a single new one that NASA is working on specifically for humans. We're looking at propulsion systems first, and then they'll start looking at, how do you put that propulsion system in the whole vehicle.
Certainly one of the other things going to the unmanned space program
Without humans
is a way of exploring the solar system. Is you want to go some places where it's kind of tricky. So for example, there's a moon of Jupiter called Europa, which is covered with ice. Underneath that ice is probably a liquid ocean of water. It would be fantastic to explore that somehow. So the question is, how do you pack up your instrumentation here on the Earth, get it on some sort of spacecraft to get it to Jupiter, to get it to Europa, to land on Europa, to test what's underneath that ice in a way that doesn't contaminate it. So that's a puzzle, and that's a challenge. And so there are people who are thinking creatively about how do we do that? Is there some type of drill I could come up with that might get me through the ice, again, without contaminating it, to see what's there? So those are all sorts of questions. And you were talking about Voyager being at the edge of the solar system. One of the things that I think is amazing about what we in NASA has been able to do is there is a mission called Cassini that went to Saturn. And it has been orbiting Saturn for a number of years. But one of the things Cassini did was it launched a small little probe that landed on the surface of Titan, Saturn's biggest moon. We didn't really know what the surface was made out of. We didn't really know what we were getting into. But this probe landed safely, upright, on time, and worked, and took pictures from the surface of Titan. And it's remarkable to be able to do that. So there's always going on to that next type of vehicle to allow us to explore the solar system.
and I can't get my car to start in the winter sometimes. Yeah, I think that spacecraft on the surface of Titan is really incredible, and we have developed a capability to do that. And the one little piece about that I really love is that the spacecraft landed on the surface, taking pictures, doing all sorts of data sensing, and sending information back to the parent spacecraft. The lander was still operating when the parent spacecraft disappeared over the horizon and it was no longer able to get a signal from the lander on the surface. The lander was still working, and it had a 5-year trip from Earth out to Saturn. It basically slept the whole way, and then 24 hours before it landed, the spacecraft was awakened, systems were checked out, and it was dropped off and landed and worked. Can't get my car to start.
One of the things I would just like to add when they talked about the sophistication of the space vehicles, the public, sometimes we get really easy about these things. We really don't think about exactly how incredible the engineering is to do this. With the space shuttle, you know, they talk about, oh, the space shuttle is all, it's an incredibly complicated piece of equipment, but not complicated in a bad way. It's complicated because it has to be. It has lots of things going on. And we got used to everything working so well that we end up being completely shocked when something doesn't go well. I know that we talk about, you know, what happens, did people die? You know, the question I didn't get asked yet, were you afraid? It's no, I wasn't afraid. I had a lot of healthy respect for sitting on tons of high explosives, but you've never had so many competent people caring about you and working on things at a given time. So that's with the shuttle. Then you talk about these other vehicles that go and do incredible things. I'm still just blown away about Voyager still sending information.
Still
What was
working.
Voyager?
Still working.
I mean, it was when I was a teenager, I think. I'm like,
4, something like
yeah.
that.
Yeah.
That's when Voyager went out, and it's still sending information back, which were incredible feats of engineering that we can use and can apply today to so many other things.
There was a question back in the back.
Hearing, I'm not sure, I don't have the name of the man in the middle, I'm sorry, but hearing you talk about the water on
Europa.
Europa.
Yep.
It's an unknown that you know you want to find answers to, and I'd like to think that scientists can, you know, that they can maybe more easily go about finding answers to the unknowns that keep you up at night. And I just want to hear the other panelists maybe get an idea of what are the unknowns that, you know, like the ice on Europa or the water on Europa that kind of tickle your imagination.
So the question is, what are the unknowns that sort of drive you or your curiosity? Motivate you?
I have so many. You want us to stay in space? Or you want to stay in space exploration? You know, I think the big one that, you know, obviously since you're a little kid is going to be, is there life elsewhere? Now, I can already answer that. The answer is yes. The problem is, can we detect it? Is it going to be something that we recognize as life, right? Because right now, most of our, when we look at life now, we're always looking for carbon-based things. So all the kinds of things when they're looking at the planets and they say, oh, we found another planet around another star and it's based right here, it's because we're looking for things that are basically going to use carbon and water in some form or another. So if it doesn't use that, will we even find it or even think to look for it, right? I think that that's one of the things that's most fascinating. You know, can I find Worf, you know, out there somewhere? That's one of the issues that we're looking for. And there, you know, the vehicles that have been to Mars looking for evidence of water, looking for evidence of life. There's vehicles that have been there for a number of different times. Those are pretty exciting. I think that that's one of the most amazing things. And then I'm going to turn it over, but I'm going to put in my other cue about this whole idea of, you know, how the universe started, and or is it consistent? Are the physics and things consistent throughout the universe? And can we make the kinds of assertions that we're making right now?
And so that's a great
Send it over
segue
to
to
you.
the question I have, is I'm deeply curious about dark matter and dark energy because of the implications that they carry for the origin and fate of the universe. So outside of the question of life, I think that's the big one for me. And you have an
Those
answer
are-
for that?
Do I have an answer? No. What I tell people is that if you want to go meet the King of Sweden and get a Nobel Prize, you come tell us what dark energy is or what dark matter is. Okay? As astronomers, we walk around and show you pretty pictures. We talk about things we know. We talk about stars. We talk about galaxies. We talk about planets. What's really embarrassing, okay, is that all of that stuff makes up less than 1% of what's in the universe. Okay? 99% of what this universe is made out of is stuff we don't know what it is. Like,
So let me
most of the are you gonna tell me?
no, I was just
Oh,
going
good.
to say.
You were telling me. I was important. So that's a great fundamental mystery. We don't know what the universe is made out of. So we have work to do.
So here's one of the great beauties of science, and this, this sense that you hear about curiosity and all this other sort of stuff. I remember going to a lecture given by Michael Turner from National Science Foundation, who was one of the early researchers into dark matter and dark energy. And I walked into the presentation understanding the universe in one way, and when I left an hour later, it was a different universe. It was just a different universe. I could look around, and the stuff that I saw going in just didn't look the same coming out. And the reason why is because things had shifted from most of the matter of the universe, being the important stuff, to being nothing, to being insignificant in comparison to everything else. And so what this said to me is that all the stuff that we know of as normal matter is simply a residue of this other big process that involves dark matter and dark energy. So instead of us being the dog wagging the tail, we're now the tip of the tail of the dog, and the dog is something that we don't know very much about. And the great thing about science, and the great thing about all of the minds that sort of engage this now, or could engage this in the future, will be engaged in the business of trying to get a sense of what that dog is like. So it's a wonderful opportunity for people to sort of pursue this line of inquiry.
And now I also, the reason why I sort of set that up is so that I can be really crass now, and I'm going to have to move all the way over. Because one of the things that is really important is to have different people looking at the information and asking the questions, because their perceptions of what is important colors all of that. Their perception of how much they know and how cool they are, and their arrogance colors a lot of their perception of how they interpret information. One of the things about this conference on women in STEM and that I talked about earlier is that very often we don't have women involved, right, on looking at these things. We may have different interpretations based on worldview. I think one of the things that's really interesting about this panel right now is, you're seeing people of color talking about astronomy in ways which most of the time people wouldn't expect that to happen. But you can go out with a lot of different perspectives in terms of how do you interpret data. The idea from back in the, I was going to say the beginning of the century, but it's actually the beginning of the last century,
Right.
where there was a determinism associated with everything had a single right answer, and then you came in with Heisenberg uncertainty principles, quantum mechanics, all these things, which other philosophies, it would not have been hard for them to look at it, even maybe have come to those beforehand, and being able to interpret it. So it becomes really critical that we don't assume that everything is answered. Now, when you hear that 99% of the universe, over 90% of the universe, we really don't know what it is, and we're hypothesizing. We may have some evidence by the tip of the tail of the dog and what it's doing, but you know how a dog's tail can be going all over the place. The only thing you know is the dog's going forward. You really don't know that much. So understand that there's an interpretation, and there's a lot more that has to be done, and we can't assume that it's all been found, because people are always coming up with a unifying theory. I've done it. What was there? I've done it all. We already know everything exists, and it's just not true. So I didn't have to move too far.
No, that's fine.
Having heard the word contamination, I want to swing back to Earth and understand the connection between your interest in sustainability and the environment works with this whole experience of being out in space and the science and technology and so on.
So just repeat quickly, what's the connection between being interested in sustainability on the Earth and having been to space?
So when I went to NASA, my background was chemical engineering and medicine, and I had spent 2.5 years working as a Peace Corps medical officer for Sierra Leone and Liberia. I was very fascinated by developing countries, tropical medicine, all the issues associated with how do you advance people and improve their quality of life. When I got to NASA, I learned much more about ecosystems. There was information that's glaring that you can see from a global scale, from that vantage point that you have a more difficult time seeing here on Earth. For example, this is just one that's just fascinating for me. The pictures that were taken during the early Mercury, Apollo, Gemini period, when you look at the atmosphere, it's yellower today. So the pictures that are taken from the shuttle, you can actually see that the atmosphere is yellower. So that means that people are having some impact. The whole idea of using remote sensing. So you can look at a vantage point high above the Earth, and you can look back down, and you can see large swaths of landscape that you couldn't have seen otherwise. So I worked with, when I left NASA, I was looking at how do you use space technologies in developing countries, which a lot of people would say, oh, that doesn't make any sense. Developing countries have issues of how do they use their land. Normally we do land surveys, right, on the ground. So you walk from point to point to point, extremely expensive, extremely timely. Yes, a photograph from space might cost $5,000, $10,000, but how much information you get on that one photo is incredible. So if you wanted to go back and revisit what was happening to lakes, to vegetation, you get that information. You have the vantage point of seeing a lot of things from far away. Even things like old riverbeds, the course of how rivers change. There's lots of information that you can get from it. So what happened with me, with NASA, was an awareness of how much we as humans have been impacting things, from climate change, from weather, all of those kinds of things. You get an incredible vantage point from being up in the air and being in outer space. And then the other part goes along with the planetology, right? So when people say, we're gonna go study Venus, it's like, oh, you're wasting money on Venus. No, you're not, because first of all, the probe was not built by the Venusians, but secondly, you have an opportunity to learn the geology of another planet. And I always think it's like a physician. Do you want the doctor who's only seen one patient their entire career and that patient is you? Or do you want the doctor who's seen multiple patients? So then we have an opportunity to see other planets and different vantage points, which gets us back over to my colleagues.
Well, I think certainly one of the things going to think about Venus, and certainly when Venus was, people started really looking at Venus in the 1960s and 1970s and realized that Venus is this cloud-covered world. The planet itself is about the same size as the Earth. And if you go back to the science fiction from the early 1900s, Venus was this tropical Jurassic paradise. Dinosaurs roaming, giant trees, rich foliage, all that other good stuff. Then came the realization that the surface temperature of Venus is about 700 degrees. Okay? Now, you can say, well, and when I ask my students, why is Venus warmer? They say, oh, it's closer to the sun. It should be a little bit warmer because it's closer to the sun. It's warm. It's so warm because of the greenhouse effect. Okay? Because what's going on in the atmosphere of Venus. So if you want to learn about different geological histories of a planet and how the cycle between the atmosphere and the geology, the importance of an atmosphere, the importance of precipitation in keeping an atmosphere a certain way, you have to study Venus. Now, if you go to Mars, Mars used to have a lot of water. Wet place, but now it's got a very thin atmosphere. Where's that water? Right? There's a difference there in what's going on Mars and what's happened on the Earth and what's happened on Venus. So we can do this comparison, and we can learn how the planets work. We can learn what's important to determining sort of these global cycles of a planet. And now we're seeing this great merging of even thinking about planets around other stars, of people who are doing climate models of planets around other stars. And trying to figure out, one of the neat things thinking about the Earth is we're kind of lucky. Okay? The planet we live on, we got a nice stable orbit. Our orbit is nearly circular going around the sun, doesn't wobble too much. A lot of these other planets we're finding, they've got very elongated orbits. They wobble a lot. That does terrible things to your climate. And so we got to think about how we want to take care of this place, because it's kind of unique.
You know, there's so many ways to sort of frame that. I think the biggest way to frame that one particular thought about the importance of the Earth and its location is that I think we've discovered now I guess the number is now nearly 900 extrasolar planets.
Yeah.
600 before the Kepler discoveries just
Right.
recently, so it's about 900 extrasolar planets. The term is loosely or cavalierly thrown around that Kepler will identify Earth-like planets. And my retort to this point has always been, there's nothing Earth-like about them, except that perhaps they're spherical. And that's about the end of it. Because these planets end up being too close to their parent star. They're way too large. They're mostly like gas giants, things of that sort. And so we have been able to identify planets orbiting other stars, and gee, that's great. But none of them are really Earth-like. Earth-like means a planet where there is copious amounts of liquid water with a nitrogen-oxygen atmosphere in a temperature range, already identified by the liquid water part, that is somewhat conducive to life as we know it. We haven't seen anything like that yet. Yet there are, of course, billions of stars, and the likelihood that we're going to find some life somewhere else is pretty good, just because of the numbers, right? But not for one femtosecond should we imagine that we are going to stumble across large numbers of, honest to goodness, really Earth-like planets.
M-class, that's what
M-class planets.
You can check
Thank you.
Thank you, Major. Yes. The possibility exists, but we should not for one moment think that we are going to identify a whole group of M-class planets anytime soon. Only because of the fact that this is a very unique situation. We have this G-class star. We have this particular planet at this particular location from that star. The environment is just right. Eric talked about the hot end at Venus, the cold end at Mars, and here we are in this one great position. You've heard the term Goldilocks position. Not too hot, not too cold, it's just right. So, what this points out, though, is probably the most important thing to come out of this exploration for extrasolar planets, and that is that this planet is unique. This planet is unique, and we must do everything we can to preserve, I don't want to say the natural order of the planet, but do what we can to protect the environment of this planet, because out of this exploration for extrasolar planets, we're not finding a planet that we're all going to sail off to in a spaceship anytime soon. We must protect this place, because for the next, how many thousand years? 100 years. The next 100 years. The next several thousand years, this is our home. This is where we're going to be.
I want to add, you talked about space exploration. What did it do for me? It's
and this goes along with everything we've just said. So when I looked down at the Earth, it was just incredibly beautiful, and looked at the stars and the moon, incredible beauty. The Earth, you look at it, has this thin shimmering layer of blue light. It's like it iridesces from within, and it affirms something I've always believed. When people say save the Earth, I think they're mistaken, because the Earth is going to be here. It's incredibly strong, incredibly forceful, but we might not be here. And we get it confused, because right now it supports our life form, but it might not necessarily do that all the time, but the Earth will be here.
Earth will be fine.
They have other kinds of hormonal cycle issues that, aren't as evident, except if you look at their behavior. But, there are lots of things that go on, but it's not, there's no big issues with that. Women have had normal cycles and stuff in space. But one of the things that I find very interesting when people start to talk about is sort of pare down who goes into space and what happens. I'll tell you that, and there's always a question, should we have women on long duration missions? Are they going to have problems with bone loss and things like that? Well, women are psychologically more stable in long duration missions and things like that than men. If women lose bone, then men are going to lose bone too. It's not that easy. But if you're going to go for that, or then you're going to say we should only send African and African American men up who have less bone, have more dense bones than others. That's not the issue. The question is, how do we produce an environment that's safe for all humans, right? That's what we're looking at, is an environment that's safe for all humans as we send people up. It's really not about this gender, that gender. But if you were to just say the most important thing is probably psychological stability, and women sort of win that hands down on long duration missions. But anything else?
No, you said it all.
Right now, there's, thank you, just first of all, this has just been amazingly brilliant and thought-provoking. There's a lot of pushback by some of our fellow citizens against science, and anxiety that discovering more things is fearful. And I just wonder if any of you have come across that in your talks with large audiences, and how you might respond to some of this, what I would call a kind of cultural fear of discovery, and of really making science, taking science very seriously in our educational system, and seeing it as a promoter of humanity, as you described.
Questions about pushback against science and sort of fear of discovery and how to respond to that.
Well, one of the big topics that's beginning to show up these days in regard to this kind of discussion about the pushback from citizens and the general public is the concept of denialism. This idea that that with very, very limited argument, one can refute the advancement or use of science to advance things or correct things. And the two most basic examples of this are the idea of genetically modified crops. The idea that our food source is being genetically modified by altering the DNA. And so the argument is we need to get away from genetically modified foods because this is terrible for us. In fact, we have been genetically modifying foods for thousands of years. Anything that's eaten today that's a grown crop has been genetically modified. The only difference is the degree to which that genetic modification is being done these days. So what we're talking about in that particular instance is when you take one plant and graft it with something else, you're genetically modifying it for better results. The other one of these is a very, very big and deep argument about vaccination and whether or not vaccination causes other problems in children, particularly with infant vaccination. But what a lot of this denialism is based on is a lack of a really deep understanding of the process of science and how it actually works and what it comes up with. And it's also based on the assumption that many people carry that science is a process that comes up with a 100% correct answer all the time, when that's not really what happens in science. Science is a progress of looking at phenomena, trying to understand parts of it, and then depending upon the work of many others to either vet this or add to it so that a more complete picture is brought up. So it's not as if the expectation of scientists is to come to one answer at the end of the road and that is the answer, but that there's always room for growth and experimentation and adding to the body of knowledge. So in our culture today, we can easily see what the place of science is. If you look around, it's so easy to see. The most celebrated people in the culture are not scientists. Yet, when you look at the people on this panel, when you look at the incredible advancements in science and technology that have allowed the quality of life to be raised to such a high standard based on science and technology, it's absolutely irrefutable that science plays the major role in making all these great things happen. But without the proper education for our children and for generations of children, it's now beginning to become evident in STEM areas, then it's easy for someone to come to an incorrect conclusion about the effect of one of these kinds of things and deny that the science is really there and working, or that you can come up with a way to deny that the science is effective and true. And the arguments that get used in this, unfortunately, are not just non-logical, but they go to a place that sort of makes it difficult to refute. And so I think that one of our responsibilities as scientists, and our overall responsibility in the culture as a whole and society as a whole, is to bolster, again, our level of science literacy. Because there's no way that we can either turn back the science, and there's no way that we're ever going to stop using the science and technology to continue to raise the quality of life for everybody on the planet.
I'm going to come from this a little bit different ways, and then I don't know whether to talk about GMOs before or afterwards, because I disagree with you a bit on GMOs. Okay. Because what we're doing as we modify things where DNA is very different when you add it in and do chemical modifications on the DNA versus grafting one plant to another. But that's a whole nother biological argument. But there is a lot of irrationality that's associated with lack of science literacy, lack of basic knowledge about certain things. But I'm going to come from the perspective of part of this dismay is because people think the world is changing too rapidly around them, and folks disregard the fact that they have an opportunity to shape science. People have this tendency to want to hold on to the belief that the physical sciences and the social sciences are separate and not connected. But they are very connected. They're based on what we decide to develop, what tools we decide. Technology are just tools. We've had tools for thousands of years, right? Technology is a tool. Science, to me, is an understanding. You can create tools with your understanding. And depending on where you are in a society, how secure you feel in your environment, your hopes, your dreams, your aspirations, your fears, those kinds of things will shape what you do with your science. So, for example, what's the difference between a mechanical engineer and a civil engineer? Some people would say mechanical engineers build weapons, civil engineers build targets. It depends on what you do with your research. One thing doesn't happen or another. You can use a certain combination of minerals to create a beautiful fireworks display or to propel a bullet. When we look at space exploration, you can use space exploration to study our environment, our atmosphere, other planets, to communicate with one another, or to assess the military capabilities of other folks, augment our own. It's really our decision what to do with understanding. Science doesn't make, the fact that an electron flows a certain way doesn't make you make a ray gun, right? It's your idea of what you want to do with it. And I think that that's the issue that a lot of people have. They've abdicated their responsibility for voting responsibly, because science literacy is so at a premium, not just within the public, but even in our policy-making officials, that we end up having this mysticism associated with it and assuming this stuff is happening one way or another, but the science doesn't make it happen. What we decide to do with it as a society. So I would ask everyone to promote science literacy. I do a lot of work through a program called The Earth We Share, international science camps. Kids that, they don't intend to be scientists, but it's important for them to know how it works.
This is one of the, I think, biggest challenges for institutions like mine. Right? So I'm at the University of Wisconsin, large state university, 45,000 students on campus. We admit 6,000 freshmen each year. Okay? The vast majority of them have taken some science in high school. But our challenge as an institution of higher education, and then it goes down to the K-12 level as well, is to increase that science literacy and instill in students an appreciation for how science works. It is not, as Derek said, it does not give you an answer. It is a process. It is sometimes a messy process. And that's actually when it's most fun, right? When you're wrestling with something, trying to figure out what it all means. When we air that dirty laundry, we get shot down. You guys don't know what you're talking about. And so one of the things, and I'll throw this back out at you, one of the things we wrestled with at Wisconsin about a year ago is that our atmospheric science department said we have some very complex models for essentially predicting the weather on a week to 14-day scale. We think it's fairly accurate. So they went to our communication arts department and our sociology department and asked the question, how can we convey to the public that we have a model that is relatively accurate, but there's some uncertainty? How can we convey so the weatherman can stand up there at the 6 o'clock news and give you a weather forecast that is scientifically meaningful and not have you call in 48 hours later saying, it didn't rain today, and you said there was a 60% chance it was going to rain. So it is coming back, how do we work together across the disciplines to engage the public in science and convey that to the public and have the public be part of the conversation, right? Have you be part of the conversation. That's what our challenge is. We don't have the answers yet, but I hope you will help us.
And with that as our charge, I'm afraid that we need to wrap up. It's been a fascinating conversation. Thank you, Dr. Mae Jemison.